I'm Mike Hawkes.
And I'm Kevin Spangenberg.
Welcome to In Between Charges, the perfect podcast to listen to while waiting for your EV to charge.
We bring you all the information about what happens in between charges, behind your charge points, and behind the scenes of the EV ecosystem.
In this episode, we'll unpack how the grid, an infrastructure that took almost 150 years to build, has to be transformed, and in many cases even rebuilt from the ground up to accommodate for the electrical revolution of large-scale industries, including transportation.
The kicker? This transformation needs to happen now. Is this even possible? We brought in Christoffer Greisen from Hybrid Greentech to answer this question and more. He'll help us understand the advent of new software, new storage technologies, and next-gen tech, and all the nuances of the grid that will react and interact with the electric revolution.
So plug in, grab a coffee, and enjoy. Christoffer, welcome to the show.
Thank you. Thanks for having me.
Yeah.
It's a pleasure.
Yeah, exactly. And we're joined by Kevin as well, our other co-host from Monta.
Fantastic to be here.
Maybe, Christoffer, could you give us just a bit of an introduction to who you are, your background, and what Hybrid Greentech do?
Sure. My full name is Christoffer Greisen, and I recently joined Hybrid Greentech, a gear-up company that is working with a virtual power plant solution for independent power producers, industrial, and a number of other industries that work with energy storage. My background is as an engineer. I've been an engineer for more than 20 years from the Technical University of Denmark, but pursuing a project management career, and I've worked in various industries such as fuel cell industry. And recently I was back in university leading a big multi-stakeholder project on the optimal operation of the combined and sector-coupled energy system. That's where I learned and understood and got an interest in the combination of technology and business development in this realm. Our mission in Hybrid Greentech is to help companies become 100% on renewable energy, and to have, you can say, 100% of renewable energy in their portfolio, and make sure that what they do, if they are an energy company, that they can get their 100% renewable out there. So we want to make the system completely green. And that requires a number of coordination efforts, because as we say in the translation from a Danish saying is that the renewable energy, it comes as the wind blows. It's fluctuating, and we need to adapt and make our energy system go from what we used to do like 20, 30 years ago was to just use energy when we could. We have to embrace that energy is now something that is, electrical energy at least, is something that is coming with the sun and the wind, and has a very interesting property. All the costs related to it is basically capital costs. So it doesn't cost you extra. It doesn't save you anything to shut down a wind turbine or to shut down a solar power plant. It doesn't save you anything. All the costs are already in the materials, in the systems, and so on. That means that we need to have completely new business models and completely new modes of transferring and trading energy.
Be great to hear your thoughts on that.
The grid, as we know, it started in the end of the 19th century with very local grids around special inventors and cities and districts where they were running on DC, basically directly with batteries, and you could get the electrical lighting. It was magic. And then you had the invention of rotating machines that could create electricity from mechanical power. Based on the beginning, it was steam, and then it became combustion engines, and you also quickly created water mills, and only later, actually, reasonably late, windmills for electricity production. But they started running DC, and then, of course, there was a need to get the power transported over longer distance. And if the audience knows a little bit about Ohm's law and so on, the fact is that the higher the voltage, the lower the losses in the transmission lines. And that's why you want to go to higher voltages for transmission. And that was actually what, in my understanding at least, drove the choice to go to AC. So, because that can be created with a rotating machine. It doesn't require silicon, basically, and semiconductors. Come back to that in a moment. You could then basically, let's say you were an industrial company, you didn't no longer have to have your own power plant to create your own electricity. You could just buy it from the local grid. And thereby the grids became more and more interconnected. You synchronized more and more grids with each other. You found out that if you had a power cut in one city, you could actually get the power from the neighboring town. There's an advantage in that. And so it became more and more reliable because you could actually buy from each other. And then you had, of course, also ownership models that developed out of that. And then you had in the 50s, 60s, 70s, the quick development of semiconductor technology, which actually means that today on the very long distances, if you have more than 100 kilometers, I can't remember the exact trade-off, but you have this high voltage DC transmission. So you actually use DC, which also means that you can transfer energy from one frequency area to another. So you don't need always to be synchronous to exchange energy. But it's still easier, and that's what we have. We then see that we have the DC connections for very long transport or for the linking up across synchronization areas. And now we have the synchronous area of continental Europe. We have a synchronous area of Scandinavia and the northern region. And actually, with the political situation we have today, it's quite interesting where the things go. And now, as some of you may have followed, Ukraine has synchronized recently with the European grid, which means that energy trade across the Ukrainian-Polish border is much easier than it was before.
If we can go back a little bit to understand essentially the background, the infrastructure of the grid and why it's kind of set up as it is today, because I think that'll be useful to set the context for what the limitations are, and then as a result, what we can kind of build from forward. And so one of the kind of topics I was thinking about earlier is, and you maybe touched on it as well, electricity is something that we consume. It's something that we just think is always there. It's ever present. It's almost consumed as if it's the air that we breathe, right? It's something that's a given.
There is a natural monopoly nature in the grid as we have it. It's obvious that there is an advantage to have a grid. You can easily imagine that you have electricity without having a grid. That happens in more rural areas. You have it in your car, you have it on your boat, now you even have it on your electrical bike with various support functions and so on. That's its own little grid. And you can say the laptop you're sitting here in front of you, where it can power up the phone and the headset and the microphones and the communication. And that's all, you can say, a microgrid or a nanogrid. And you can envision that, and that's the ultimate consequence if we don't collaborate and have a grid to transport power. And most analysis shows that in most inhabited areas, it is an advantage to have a grid. And historically, the grid has some properties that we have inherited from our ancestors, just like the roads, just as the buildings. There's the frequency is not something we can just sit down in a committee tomorrow and then decide to change from 50 to 60 hertz in Europe or the other way around in the US, or the voltage. That would not be possible.
I think you touched on something there that I was very curious to ask you about, which is individual grids and how certain grids set out to be on their own. And you have the liberalization of certain grids, maybe a Texas that wants to chart their own path and go forward. And then other larger intrastate or international grids that are sending power across great distances. And so you hear the microgrid, the term, and you talked about how a laptop could be its own microgrid. And then you go scale up to a building or a household or an apartment or a hotel. And then you have the larger supergrid that can connect power, that sends power from Norway down to Portugal, for example. Is going forward, do you think that the way that we produce and consume power is going to continue to be a mix depending on the local needs? Or do you see kind of one model with maybe millions of microgrids kind of winning out? Or is this supergrid always going to be necessary to produce and send power where it is needed?
I certainly think that what you call the supergrid, the transmission network, is going to continue to be relevant.
If we talk around, I want to understand then what we mean by storage, which is efficient and useful, versus storage, which is the opposite. Because storage is always kind of heralded as this holy grail solution to fastening how we can actually get electrical energy, and we can transmit all the electrons basically to all of the different cars and different uses. And large-scale storage that's using energy from various different sources and areas can also help to cater for significant shifts in renewable energy provision, if we know that that's more unreliable, for example. So can you help me understand that a little bit more? Like, what's good storage? What's bad storage? What are some of the best ways that we can use that to help? transition?
We're actually not interested in electricity. We cannot use electricity for anything, basically. The electricity is a means to transport power and energy that will do some kind of work that creates use for us as humans. So it allows us to communicate. It allows us if it runs a heat pump, it can provide heat or just resistive heat or cooling, whatever we need to. And there's a lot of energy consumption in that. And we should basically look at the energy system, the power system, as something that can help us to get our natural resources to provide the work and the services that we need as human beings. And that can be mobility, it can be comfort, it can be cooling of our goods, it can be all kinds of services. And when we look at that, there are many ways of making that efficient. And electricity, for example, it's very efficient in terms of driving machines. You can get efficiency around 95% from the electrical input to the measured mechanical output of some kind of electrical machine. They're very efficient compared to internal combustion engines.
But the topic around the efficiency of your battery and how that degrades over time, is that really significant? Is that something that we really think will change the cost of the car? How many batteries are actually recycled or reused? How often you actually might need to put additional amps or kilowatt hours into your battery that will give you a much lower range, for example? Because I think we see so far over the course of maybe 10 to 12 years, it's relatively negligible. It's like 10 to 15% or so.
I certainly think that there's so much research and development going on with battery technologies, and I think we have seen significant improvements both in battery management and in battery chemistries themselves. We have a lot of top-edge research and competition on battery technologies. I'm not at all into all the details. I have worked with fuel cells, so I know a little bit about microstructures and some of the fundamental mechanisms that degrade these microstructures. But I think it's definitely going to improve, and so are other storage technologies. The only thing you should, as a normal power or electricity user, be aware of is that there's just no free lunch. There's the battery materials and all the supporting equipment. There's the investment of it. There are considerations about the lifetime of the power electronics.
But of course, we work in the EV space, and we know that's, while it is energy intensive to get these metals out of the ground and to transform them into a battery that can power your car is energy intensive. We do know that the total emissions throughout the lifetime of an electric vehicle are far lower than that of an internal combustion engine. So that's a common, I think, refrain among people that are hesitant or resistant to these new renewable technologies that we need to adopt. You mentioned something earlier, the virtual power plant. And that's a word that we hear, but the layman, the average person might hear that and might be a little bit confused because it can be contradictory. When I hear virtual and then power plant brings to mind what the smokestacks that we have that we look out from our office here in Copenhagen. And virtual is, I think of a platform, I think of the App Store, whatever it might be. Can you talk about what a virtual power plant is, in the kind of the clearest terms, and how that is going to, in your opinion, transform our grid and how we interact with the grid going forward?
Well, a virtual power plant is actually a term that has been around in the industry for quite a while. Personally, I encountered it first when I worked in the fuel cell business, where you could bundle small micro combined heating and power plants. Combined heating and power plants are basically running on gas in an individual household and producing for that household. And then the virtual power plant is an aggregation, a collection of many small units whose consumption you can control. So usually as a power company, we'll look at the balance in the grid and say we increase our power production to create stability, balance between supply and demand. If you look at the grid, you can have exactly the same impact on the grid if you reduce consumption as if you increase production. So you can actually create a virtual power plant with only consuming units. As long as you know that you have a certain part of your portfolio that is always in operation, then you are actually always able to regulate up or down. And then that creates a bandwidth that you can offer. So when you model the entire energy grid, you can think of it as a power plant and think of it as a unit that can be plugged into your models, just as you plug in and sit at your old-fashioned desk and say, let me see, I want a nuclear power plant here, then I want a big coal-fired power plant there. Of course, it's not exactly the way that the energy system is operating now, where you have so many different and individual units. But of course, we still use it for historic reasons. The virtual power plant is still a powerful term because it has a size so that it can act on the markets and on the infrastructure for big power actors. You can say there's a realm where the energy system is discussed and traded, and the balance is arranged between various large players that all work together in order to make the electricity grid work. And on this playing field, you have traditional power plants. They have a smokestack and, in many cases, an associated district heating network.
So is it fair to say, in a summary, the virtual power plant is something similar to an operating system that will help to manage consumption with demand and also balance various different inputs in substitute of a power plant, but a necessary input is that you're still getting it from a network through lines. So there is still a physical element to it. It's just the operating system that runs.
Everyday user can be part of a virtual power plant. So you can envision that your electrical vehicle can be bid in. You can offer it, and there are already options where you can have now you work in the electrical vehicle business, and you can say surrender or give away the control of your unit to an external actor who will then bundle it with other units and create an impact on the bigger grid.
Also having micro or even nano grids, and we can call it whatever it is. The virtual grid essentially is a way to try to perhaps aggregate some of these new sources of energy, batteries essentially, that are perhaps mobile of various different sizes. Obviously, we're kind of in the EV space. A big topic at the moment is vehicle to grid. How do we actually start using a battery that perhaps has excess charge to be able to provide that service? And it could be on an individual level, but also very interesting to understand it on a community level. So you create this micro community where everybody is kind of serving each other in a very kind of specific way. So if that's an example of one kind of new service that, well, the virtual grid has been around for a while, but it would be used differently. It's going to evolve based on new technologies that's coming out.
Some of the services that are available today and traded is, of course, invisible to the individual user. But I would say most of the individual users know that we're getting an AC current out of our plugs, and it's running on in Europe 50 hertz and 230 volts, and it needs to keep that frequency. And that's, of course, in the synchronous areas. Electrical current is running its plus and minus with a 50 hertz, and it should be completely in phase. And it should not drift. When it's drifting away from the 50 hertz, it's because there's an unbalance. That can be detected by anyone who can buy a frequency meter. And then you can actually provide a service that either injects some power into the system or pulls out some power from the system. That's important because you don't need a control signal from some superior entity to actually deliver that service. You can do it based on your own measurement of the frequency. And then you have assets that can regulate up or down. And I'm not going to go into details about how they're constructed and how fast they should respond. And I think we should go into a more specialized. But the basic principle is that whenever there is a drift away from the 50 hertz, various actors will react. And that can be, traditionally, it would be completely passive. It would be the turbine in a power plant that, because of its own inertia and its mechanical coupling to the generator that's essentially creating 50 hertz, it would actually, because of its own inertia, it would bring the frequency back on track. And then the power plant operator will detect that now the generator is getting loaded, so you would have to chunk up the fuel supply and basically press the pedal a little bit more on the power plant. That's the traditional way to keep the frequency in control. We're getting less and less of these types of assets in our grid. We still have some. So now we have other assets that can do the same. And that can be consumption. And in principle, it can also be done with a group of EVs.
Yeah, so I guess if you could talk about the ways that's changing, because that's the kind of the classic way it's been done, and you now just alluded to the many ways that is changing the way that we're all interacting to the grid and the way that we're feeding the grid, or who and what is feeding the grid in that way. And maybe talk about kind of the way that the traditional business model of the transmission providers or the utilities are being disrupted and how they're responding to that as well.
Yes, at the transmission level, there is an architecture of this market which is unified across Europe, where these services they look similar. They're not completely identical, but there's a common architecture where you have auctions for these services, and you can then have a competition, and you can have a market mechanism that finds the most cost-optimal way of achieving this stability service. But you have other places where it's, you can say, an old-fashioned command and control way to do it. And we already see with new consumption and production, big stresses to the grids, because you have, as you can imagine, a large solar park that is producing 2 megawatts in a local environment, and then suddenly a cloud goes over it, and the production from that drops to 1/10 within minutes. And that is really stressful for the local grid. And it needs to suddenly shift and pull in energy from neighboring transformers and so on. And that is where I can envision that you will have, if you can create new business models where various local stakeholders can then react to this and stabilize also, for example, the local voltage. You can imagine that the grid is, of course, quite complex, but in some areas you have a long line, and you will see that the voltage level at the far end, far away from the transformer, is actually a little bit lower than close to the transformer, because basically some of the energy is lost on the way. So you don't have the same power. That's what you call power quality. And today, this is not marketized, you can say. There's a certain service level, and the distribution system operator is guaranteeing that you're getting that out of your plug. And we'll see in the future, I think, that it will be beneficial to harness the self-organization of market mechanisms to do that.
When we talk around the monopoly that utilities ultimately own came about as a result of, yes, we have these growth of this kind of micro communities, small grids. As that expanded out, public legislation for them to be able to work together to essentially be able to fuel increasing electricity demand. And I think we saw massive uptake essentially after World War II to be able to support the industrialization and all of these mass production of automobiles, whatever it might be, weapons, equipment, etc. Now we kind of see essentially a big threat to that model, or at least utility companies would see it as a threat, because we say smaller communities or players are going to have a role to play in that. And in many different ways, they will have different price points, different products, different services that are attractive to a consumer. And also they have then much more of a choice. So I guess what's your point of view, perhaps a step out from the transmission operators, then through to the utilities, around how this will change more of the customer-facing business model and product?
We already have on the liberalized market on the electricity production and consumption. We have a natural monopoly on the electricity distribution. And that's, I think, this is the frontier where the transformation is going to happen. So you don't see, and you actually have the regulators, which are the entities that are looking after the natural monopolies and ensuring that they don't abuse the monopoly status, is very much aware of this situation, that the owners of a distribution system or the actual grid can exploit their monopoly situation when they go into other services. Because, of course, when you have access, and that's why actually what you'll see is that the distribution system operator is not allowed to contact the customers themselves. So they don't own the customer. That's the retailer. Actually, the distribution system operator is a supplier to the retailer and allowing the retailer to get their electricity out to the customer.
And so as these utility companies are disrupted, as these business models are changing, will that change what they offer and change the way consumers consume electricity?
We're talking a lot around increasing electricity consumption, but also the demand for it to be ever reliable and essentially not change from the reliability of today. But before we get into some of the services or perhaps the way the grid is actually set up, it'd be useful to understand where it came from and how we essentially came about this completely interconnected power grid, both at the intercontinental level, but also within countries. So what's one book that you would recommend to listeners wanting to learn more?
Yes, I would really recommend a book called The Visual Power Grid by Christian Dale Winter. that is going through all these topics. And the reason is not that I read it myself, it's because I saw it on the desk of one of our new colleagues who came from a different sector and needs an introduction to the sector to make his impact.
Christoffer, from your experience with Hybrid Greentech, what are 3 of the most prominent conversations that you're currently having in the market, either with new or pre-existing players who want to play a role in or are being disrupted by this transformation?
Well, the very interesting part is that as we go away from big power plants that need to be designed big to be efficient and to be environmentally friendly and so on, and go to technologies that in their nature don't need to be big. And that is batteries, fuel cells, solar panels, to a certain extent also wind generators. I think actually wind goes towards bigger and bigger units and players that are able to deal with them. But solar is, I think, has a very good place with a very distributed and integrated nature.
Then I think the only thing let's say, Christoffer, thank you very much for your time and for coming on the show and also sharing your experience and insights into the grid, but I guess also the challenges that we'll face over the course of the next 10, 20, 30 years, whatever it might be, and also potential opportunities for businesses to either enter into or play in the space. Thank you very much.
Thanks for having me.
Thank you, Christopher.